structuring machine learning pipelines such that you explore all the different aspects that can potentially influence the accuracy of your model, and such that the pipeline itself is dry, which stands for don't repeat yourself, so that you reuse your code as much as possible. So typically, there's a typical workflow that happens in data science. Data scientists work in a Jupyter notebook. They import some static data set, they process it somehow, and train and tune the model, either using just intuition for the hyperparameters or using something like grid search or random search. And often productionization is a separate step. So either the data scientist hands the notebook over to an ML engineer, or they are themselves responsible for productionization. Which is fine, but there are a few issues that come up. For example, it could happen that some of the code that you wrote in the notebook, which does some pre-processing on the data, is different than in the production version. If there's a separate step between the two, then you could end up training a model on a different data than ends up in production. And that leads to essentially poorly performing models, and it's a silent failure. There's several manual steps associated with deploying a model. So if you have a huge number of models that you're deploying, this can become a bottleneck. Every time you have human intervention, then there's scope for error. Often these notebooks contain several different aspects about training a model, is pre-processing, training, etc. That leads to code that is not very well structured and well reused. And often the code in the notebooks is not scalable. It's a single process thing which works for small data sets, but ideally you would have something that scales to larger data sets as well. And data scientists do a huge number of experiments in the notebook, but eventually what they deliver is a single model with a single set of hyperparameters, and you don't see their work up till then. So if a new data scientist comes along, they don't know what didn't work, they only know what worked. So when we talk about optimizing a model, there's three factors that we consider. There's the features, which can come from different input modalities like image and text. These inputs are transformed using pre-processing. There's the model with its architecture and the different training objectives that you optimize for. With classical machine learning, you usually just have a single objective, but with deep learning, you can do multi-objective learning as well. And then there are hyperparameters, which are parameters that you don't learn from the data, but you set, which influence how the model works. And actually, I would call it a quadruple because all of those three factors are highly specific to the data sets that you use to train the model. What kinds of labels it had, what kinds of distribution it had. So let's take a contrived example. We have here, assume we want to build a model solution which crawls the web for PDFs of people's CVs, and we just predict from the raw text of those PDFs what profession the person has. And then we define these different sort of classes and subclasses of professions. And here you basically have 5 different training objectives. You have the industry objective, which has 3 classes. You have AI objective, which has 2 classes, and software objective, which has 4 classes. And then you have finance and construction objectives, which, like, I didn't list all of the classes that they have. And there's 2 ways in which I can use this sort of tree of training objectives. I can either do multi-step models or multi-objective models. So in the multi-step case, we train 1 model per training objective. Let's call it industry. And then essentially you have 1 separate training data set per objective. And during prediction, you start with a sort of lower level training objective, get a prediction. And if the prediction is for something which itself is a training objective, then you use the following training objective model to make a prediction. So in this case, potentially, you pass the same data through 5 separate models. In the multi-objective case, you use a single model. In this case, it has to be a deep learning model. As far as I know, there's no other kind of multi-objective learning. But this model has several output layers, 1 per training objective. So if you have, like here, I'm only showing 3 actually, the training data set is a concatenation of the previous 5 training data sets. And now if a data point has a label with respect to a training objective, then the model's parameters are updated across the entire model and only the top part of the training objective, which is specific to 1 training objective. Similar for the AI objective, and it could happen that a single data point has two labels with respect to two data sets. But always the middle parts of the model gets gradients from all the different training objectives, which effectively means that the lower layers or the middle part of the network sees a very large training data set, much larger than in the case of multi-step models. And if the training objectives are related in some way, then it can lead to better generalization, especially in cases where one of the smaller objectives doesn't really have many labeled data points. But it's not upfront obvious which training objectives should you optimize together. So it would be good to have a flexible system for trying out these different combinations, because there's a huge number of combinations and hyperparameters, etc. So I propose that you define these simple configuration objects, which later your pipeline uses. At the core, there's a model configuration, which is configured to use a dataset configuration object. The model is optimized for one or more training objective, and the dataset contains data points with labels from one or more training objectives. The model also has one architecture. This could be LSTM, logistic regression, transformer, and is able to operate on certain kinds of input representations. So this is probably not readable, but I'll describe what's going on here. So here we define the tree of training objectives that we showed before, and you have three kinds of objects. One is a multi-class objective, in which case the training, so the output layer that you build for a deep learning model will be a sigmoid layer, and you always pick one class as the predicted class. Then you have multi-label objective, which means that for the deep learning model you build a sigmoid output layer, and each and every one of those output units can predict true or false, basically. And then you have ordinary class object, which means that this is just a class, it's another training objective, which means that it's a leaf node in the previous tree diagram. Then you define what goes into your data set. You give it a name. You say what kinds of labels, like data points with what kinds of labels should go into this data set. What kind of transformations should you apply to your data set? So these are defined as the mapper functions. And what kind of filters do you want to apply to your data set? Maybe you want to filter out data points that don't have a title or too short. You also define what kind of query you will use to populate the data points in the prediction set. This could be something like everything that yet doesn't have a label, or something more sophisticated for active learning purposes. And then you define the columns that are present in the data set. This is just for documentation purposes, but also acts as a contract between a multi-step pipeline where one step writes the CSV and the other step reads the CSV. Then you define an architecture where basically you define what kind of implementation does this architecture have. So you just pass it a class name, which later gets instantiated once you actually have the model, when you build the actual model. You define what kinds of input representations it works on. So this is a transformer, so this one only works on text. And what kinds of hyperparameters and default values this architecture has. And finally, you configure a model to say which architecture it has, which objectives it's optimized for, and what kind of input data set it has. In this case, I also show that you take the input data set, which is the software data set we just defined earlier, but you only predict for data points where the language model predicted English. And finally, there's a helper function from this. Actually forgot to mention, I'm planning on open sourcing this, so you can use these sort of objects that we defined, and you get this helper function which helps you define this pipeline for you. So what it essentially does, it builds the pipeline into a YAML file, which is a Kubernetes object, which you can upload into Kubeflow pipelines UI. And this gives you a way to trigger different versions of this pipeline. So this is a screen for when you trigger a pipeline, it shows you some input parameters. And the previous line, which I just showed, makes sure that the hyperparameter values of your architecture are going to be the input arguments to your pipeline. So you can trigger a pipeline with different sort of model hyperparameters. And if you look at the UI of Kubeflow pipelines, this is what the sort of entire pipeline looks like. So you create the data set, you train the model, you export the model, predict for the predict set, evaluate on the test set, and if the test set accuracy is high enough, you deploy the model. And this is what it looks like if you start executing the pipeline. Each one of those boxes is basically a Kubernetes pod, so it's a containerized environment. It can write to a shared storage so that the next step can read the data from it. And there's some sort of conventions that are implemented in the open source software as well. And this is a version of our pipeline that finished. So in each of these steps, the pipeline uses these configuration objects that we previously set up. In the create datasets step, it uses the objectives defined on the dataset configuration to determine which data points do you want to dump. Then it does some pre-processing, which is parallelized using Dask across multiple cores or multiple machines, applies the mapper functions and filter functions to derive the final data set. And it also uses the predict set query to figure out which kinds of data points go into the predict set. Then the model train takes the model configuration object, looks at what is the architecture defined on it, and instantiates that architecture. It passes in the arguments that we just saw in the previous screen, which are the current hyperparameter values that we're going to use for this model. So in the TensorFlow case, for example, the model function could be the thing which builds up this computational graph for you. And now you can also look at the model configuration object to see which kind of output layers do you want to build for a neural network. And then it goes through the whole process of training, evaluating every once in a while. And when it's done, then the export model step looks at the different checkpoint values that the previous step created and exports the model with the highest tested accuracy. By export, I mean it just like outputs some configuration value to a table or something like that and copies the model files to a special location. Now the model predict stage can pass through all the data points in the predict set, and in parallel, the model evaluate step can evaluate the model on the test set. What's important here is that once it gets the accuracy of the test set, it records all of the values that you have in the configuration objects. What was the architecture, hyperparameters, which input transformations did we apply? Because those are all the things that could eventually influence the model accuracy. So you want to store them in a single place so that later on you can go back and see what worked, what didn't, plot different hyperparameter values across each other. And then finally, if the tested accuracy is good enough, you deploy, which can mean several different things. And I recommend there's a good talk later today about the rendezvous architecture, which talks about good ways of deploying things non-destructively. But as you noticed in the previous slides, we defined this model which operates on a data set, but only in the case where the predictions, when the predictions of an upstream model, the language model, were of a given class. So let's imagine a case where we want to train two models at the same time. So we have one data set from which we train two models, but we basically want to trigger two separate branches of this training. So on the left-hand side, you see the language model training steps, which are the same as before, and the right-hand side, you have the software training objective steps. But there's a dependency between basically the model predict for software objective and model predict for language objective, which means that to predict for the software training objective, I want to get the predictions of the language model objective, which means that it has to finish before. So yes, overall, I think this is a fairly good sort of solution for especially companies that have one large data set, which is very useful for them, and they want to try out very different models, different ways to combine training objectives, different hyperparameters. It's easy to add a model, you edit a configuration file, and then everything else follows from it. Most importantly, everything that can influence accuracy is tracked, so you can look at it later. There's a lot of code reuse. There's a few manual steps to put stuff into production. And since you always record the Git revision, which was used during the training of the pipeline, your experiments are repeatable because you basically record everything that was important to the execution of the pipeline. It's scalable in the sense that the preprocessing runs across all CPUs of your machine, and it can be run across a cluster of machines. So flexible, not entirely sure. So the main flexibility comes from you not being locked into using these configuration objects, because at the end of the day, each step in the pipeline is a Kubernetes pod, and you can get to decide what goes in there. So if it's useful for you to use these configuration objects, you can do that. But if you have like very specific demands for pre-processing or training routines, then you can go outside of it. But I still think that adding these sort of trying to structure your pipelines in this way increases code reuse. And there's a few extensions which I'm quite excited about. For example, Snorkel. The idea of Snorkel is defining labeling functions rather than manually labeling data points. So the labeling functions take in the original input. It could be the text of the document, and then based on some heuristics, it outputs a label. And if you write like dozens of these functions, which can take you maybe a day or so, you can effectively label a very large part of your data set. And this can be very useful for the cases where you don't have any data yet, and then you just want to bootstrap your training process. And then later on, you can manually add labels as needed. But there's a very logical place where you could plug these labeling functions, which is in the dataset configuration. Another thing, all the pipelines so far have been batch pipelines, and there is some inefficiency in it as well. For example, waiting for one predict job to finish completely before you run the next predict job, because the one predict job, if it's a very large data set, it could take like 12 hours, and then you're just waiting for 12 hours for nothing because the first predictions are already out. So there is scope for parallelization there as well. And sometimes you have obviously real-time models rather than just batch models. In this case, it would be very useful if you could use something like Seldon, which allows you to define computational graphs, but each node in the graph is essentially a model. So you could do these multistep models or multi-objective models defined by Seldon. And it would be great if you could use the same configuration objects as defined earlier to build up this graph. But I'm not entirely sure if that's possible or not. And very surprisingly, I'm ahead of time. So if you're interested, then I hope to be open sourcing this thing. And there's more details when I do that. All right, thank you.